Time for us to do some practice. We're going to be doing trig substitution and partial fractions and some applications with those. It's going to be fun. Oh yeah! So let's start with number 1. Find the area of the region in the first quadrant that is enclosed by the coordinate axes and the curve y equals the square root of 81 minus x squared over 9. All right. Well, before we get into the calculus part of this, let's make sure we understand what this problem is asking. Of course, we know what it's asking for. It's asking for area, but we'd like a little bit more insight into area of what? What is it we're after the area of? And so we can rewrite this expression into something that might be a little bit easier to handle, or at least a little bit easier to understand. So let's multiply across, get rid of our fraction. So 9y equals the square root of 81 minus x squared. Then we can square both sides. 81y squared is 81 minus x squared, or x squared plus 81y squared equals 81. And now if you divide everything by 81, I know I'm putting fractions back in, but I'm doing it for a very particular reason. And we note that 81 is 9 squared. This is x over 9 quantity squared plus y squared equals 1. Now, what does that tell us? Well, what it tells us is the following. What we have is an ellipse. And in the y direction, we're going up by 1 in both directions from the origin. While in the x direction, and this will not be to scale, but imagine I could draw things appropriately, we're going 9 in both directions. So these are our two different axes. So we have an ellipse. And whoop. So what are we after? Well, we're after the area in the first quadrant. So in other words, we're after this part. So that's what our problem is asking us. Now, before we start, we'll go ahead and say what the answer is. And then we'll do the problem like it wants us to and say, aha, see, that's the answer. They might say, wait, how can we do the answer? Well, suppose it wasn't an ellipse. Suppose I said, hey, what if I start with a unit circle? So it's 1 in each direction. And you said, oh, unit circles. Yeah, I know unit circles. Some of my best friends are unit circles. Say, yeah, cool. How much area is there in a unit circle? Well, pi r squared, so pi. So how much area is there in this? 1/4 of a unit circle. Pi over 4. Now you might say, well, but how does that help us answer this? So how do you go from a circle to an ellipse? Well, the answer is you scale in the two directions by the corresponding amounts. Now, in the y direction, there's no scaling going on. In the x direction, we scale by a factor of 9. So it's like we're just taking our page and stretching everything so it's 9 times bigger in the x direction. Okay, so how does that help us? Well, what happens to area if you stretch it? It goes up by the same amount. So, in other words, if I stretch by a factor of 9 in the x direction, then I'm going to multiply my area by a factor of 9. So that tells us if this area is pi over 4, then it must be the case that this area, which is we just stretch in one of our directions by a factor of 9, this must be 9 pi over 4. So this is our answer. Now, let's find out. Okay. And if we did that, we want to get the points. Because they're like, oh, calculus, you must calculus, ah! But, there are other ways to solve problems than just calculus. Okay, so now that we have a better grasp of what's going on, we say, okay, area. How do you find area? Well, you integrate height. That's our height. And we now know we're going from 0 to 9. In general, we just say, well, what makes that part 0? Okay, so our area is going to be the integral from 0 up to 9 of square root 81 minus x squared over 9 dx. Okay, now we have a trig substitution coming up because we see a square root, and that's not a perfect square on the inside, but we want to make it a perfect square so we can get rid of the square root, and that's the philosophy of trig substitution. So as we look at this, we say, Well, inside the square root, we have 81 minus x squared, or we can think of it as number 9 quantity squared minus x squared. And then we're like, oh, this is good, because this is one of our forms, number squared minus function squared. And we say, oh, okay, so that means our a is 9 and our u is x. Now, when we see a squared minus u squared in our square root, that tells us, hey, you should make the substitution u equals a sine theta. So for us, we place, well, u is x and a is 9. X equals 9 sine theta. Okay, so that's our substitution. Now, we have to account for everything. Well, what's our dx? 9 cosine theta d theta. All right, well, that seems reasonable. What can we say about the square root of 81 minus x squared, right? The whole reason we're going down this rabbit hole, well, that's square root of 81 minus, and then you square this, 81 sine squared theta. Okay, well, that's the square root of 81 times 1 minus sine squared theta. You're like, okay, but what is that? Oh, that's the square root of 81 cosine squared theta, which is 9 cosine theta. Right, and that's the reason we do this substitution, is to get rid of our square root. Okay, so we can take care of that square root. We can take care of that dx. We should do our bounds. All right, because remember, these are x bounds. We don't want x bounds. We're going to go to theta bounds. Once we get to theta bounds, then it's always looking ahead. We don't have to look back. So we say, well, we know x equals 9 sine theta. So we just put in. Okay, so when x equals 0, that says we need what? We need 0 equals 9 sine theta, or sine theta equals 0, and that happens at 0. Yes, good. What about x equals 9? Well, that says 9 equals 9 sine theta. So sine theta equals 1. So when does sine equal 1? And the answer is pi halves. All right, good. So we've written a lot of stuff down, but this is all helping us to update our integral. So now we update our integral. And we say, okay, what do we have? Well, we have that this is equal to the integral and our new bounds, 0 to pi halves. Nice bounds for trig. And the square root of 81 minus x squared, 9 cosine theta. All right, good. So 9 cosine theta over 9. Yeah, over 9. And that dx is 9 cosine theta. Well, okay. Cancel the 9. And you can pull a 9 out of the integral. So this becomes integral 0 to pi over 2 of, we have a 9 in front, cosine squared. Ah, good. Progress, progress. Now, this looks mildly intimidating, and this not so bad. Well, why? Well, we have ways to integrate trig functions. At least we have ways to integrate some trig functions. So what's the integral of cosine squared? Well, to do that, we say, hey, we can do power reduction. So we're going to have 1/2 1 plus cosine 2 theta d theta. So this is our power reduction formula, and very convenient to know if you're ever going to encounter something that needs to be reduced. So in other words, whenever you have both sines and cosines to even powers. And now we're looking great. We're ready. We're ready. So we can pull out the half again. That's a constant. So we have 9 halves out in front. And then we say, all right, we have 9 halves. Now, integrate. Integral of 1, theta. Integral of cosine is a positive sign. So there's going to be a positive sign. And now, don't forget to account for that 2 on the inside. That affects it. So how does it affect it? You put a half there. Essentially, it's substitution, but it's accounting for the chain rule, because that's where substitution comes from. Okay, now evaluate from 0 to pi over 2. When we plug in pi over 2, we're going to have 9/2 times pi over 2, and then we're going to have sine of pi, which is 0 times half, so plus 0. Subtract 9/2, plug in 0, 0, and plus sine of 0, which is 0. Well, it's really 0 times a half, but that's still 0. It's hard to recover from multiplying by 0. And, beautiful, gone, gone, gone. 9 over 2 times pi over 2 leaves us with 9 pi over 4. Wow. Who would have thought? 9 pi over 4. What an answer. What an answer. Well, that's what the geometry tells us we should get. But it's good to do the calculus. And, it helps us know, hey, this thing, it really works. All right, let's keep going. Find the integral x to the 5th over square root of 9 plus x squared dx. All right, well, we can hum and haw, but we say, look at this. There's a square root there. And so we say, all right, we see a square root, and it doesn't have a nice thing on the inside. And so we're liable to think, maybe a trig substitution, not such a bad idea. Not such a bad idea. Okay, so let's figure out what's going on here. So looking at what's on the inside, we have 9 plus x squared, or if you like, that's 3 squared plus x squared. Now that takes the form of a squared plus u squared, where the a is 3 and the u is x. All right, well, that's a promising sign. Now, when we see a squared plus u squared, that says the kind of substitution we should make is u equals a tangent theta. So we're going to make the substitution x equals 3 tangent theta. All right, good. Now, to help us make all the updates, we should record what is dx. Well, the derivative of tangent, secant squared. So we have 3 secant squared theta d theta. All right, good. And what's going to happen to the square root? Now, with practice, you start to know what's going to happen, but we'll go ahead and just work it out, just so we can help develop our practice. So x squared would be 9 tangent squared. Now here we can pull out the 9. So this is the square root of 9 times 1 plus tangent squared. And we say, hey, well, that's really the square root of 9 secant squared, which is 3 secant theta. All right, so all our pieces are in place. This is not a definite integral, so we don't have to worry about the bounds. It does mean we'll have to worry about going back at the end, but for now, let's move forward, and at the end, we'll go back. Okay, so we have to update everything. So the square root of 9 plus x squared becomes that 3 secant theta. Okay, so this is integral downstairs, 3 secant theta. X to the power 5. Well, x, there's a 3 tangent theta, so that's going to be a 3 tangent theta to the power 5. And now dx is 3 secant squared theta. Okay, so that's 3 secant squared theta d theta. Well, what can we do? What can we do? Well, we can certainly cancel off one of the 3's. We can also cancel off a secant. And then we have 3 to the 5th, which of course we all know is 243. Because who doesn't remember that, right? Powers of 3, right? 3, 9, 27, 81, 243. Beautiful numbers, beautiful numbers. All right, so 243. Then we have the integral tangent to the 5th theta secant theta d theta. Now, at this point, we tend to say, okay, if you see an integral with tangents and secants, you sort of start doing a mental computation. And you say, can I pull off a secant squared, or can I pull off a secant tangent? It doesn't look like we can pull off a secant squared here, because there's only one secant. But we can pull off a secant tangent. So let's do that and see what that gives us. So we say, all right, if we did that, so that would be 243 integral, and then we would have tangent to the fourth, because I'm going to pull off one of those, secant theta tangent theta d theta. Now, our idea here, what we're trying to do is set ourselves up for a nice substitution, and we're pulling this off and to say, aha, this is going to become our du. Now, you might say, well, what does that mean? Well, so it turns out secant tangent is the derivative of something nice. So in particular, if you let u be secant, the derivative is secant tangent. So it's like, idea. Now we have ourselves a question. Question. Can we rewrite with secant? Now, if the answer is yes, then we're in great shape, because then it says make a u equals secant, there's a du, life is good, and it's a party time, because we can integrate. If the answer is no, so let's see where we're at. Well, good news. Do you notice the power we have? It's the fourth. What's true about 4? It's even. So really, when we see this tangent to the fourth, we're going to think of it as tangent squared squared. Now, why does that help us? Well, there's this basic principle that says a tangent squared is basically a secant squared, because there's this identity, tangent squared plus 1 equals secant squared. So I can swap out tangent squared and secant squared, and I have a little plus or minus 1 going on, depending upon how it works, but I can exchange. It's like the law of equivalent exchange, right? I can move things around as long as they're the same expression. I'm just rewriting it in a different way. Okay, so thinking of this as tangent squared squared, so we have 243 integral of, now what is tangent squared? It is secant squared minus 1. Okay, so this is our, now I should have made a note here, this is our tangent squared. All right, there we go. There's the note. Okay, so we've made our note. So we have our tangent squared squared. Okay, good. Now we're ready. And from here, we know how the problem is going to go, so we just have to follow it along. And it should work itself. We say let u equal secant theta. Then we say du is secant theta tangent theta, d theta. And so what we have is that this is 243, the integral of u squared minus 1 squared du. All right, good. Okay, well, we're getting much more comfortable. We started with something which looked terrible. That was algebra. We did a trig substitution. It looked a little bit not too terrible. And then we said, aha, rewrite it again. Now we're back to algebra, but much friendlier. Not a square root in sight. Nice. Huzzah. Ah, this is wonderful. Okay, so this becomes 243 integral. If you expand this out, do your foiling, you get u to the fourth minus 2u squared plus 1. All right, so that's 243 times 1/5 u to the fifth minus 2/3 u to the third plus u and plus c. All right, are we done? No, because we didn't start with u's, right? We started with thetas. Okay, so we go back to theta. So we know that u is secant theta. So that's 243 1/5 secant to the fifth theta minus 2/3 secant cubed theta plus secant theta plus c. Okay, now we're done, right? No! The fun continues, because we didn't really start with theta. We really started with x. Ooh, okay, so now we have to say, all right, what's going on here? Well, remember, we'll do it down here. We said that x equals 3 tangent theta. So tangent of theta is equal to x over 3. So write it as a fraction. And then we say, well, draw a triangle. And when we put theta in the corner, we say, well, tangent, if we channel our inner SOHCAHTOA, is opposite over adjacent, x over 3. And the missing side follows from Pythagorean theorem. It's what caused the original substitution. Now, we say, look at the triangle. And we say, okay, I am looking at it. How do you find secant theta? Well, secant is the flip of cosine. Now, cosine is normally the adjacent over hypotenuse. So flip that, hypotenuse over adjacent. Square root of 9 plus x squared over 3. All right. So that leaves us with, and here we go, our last update. 243 times 1/5 times square root 9 plus x squared over 3 to the 5th power minus 2/3 square root 9 plus x squared over 3 cubed plus square root 9 plus x squared over 3 and plus c. And that is great. Could we simplify? You betcha we could. Do we want to? You betcha we don't. No, there's things we could do. 3 to the 5th, again, we've seen that before, is 243. So if we multiplied it through, we'd get some cancellations. And even the square root of 9 plus x squared to the 5th, you can rewrite that. All right, so there we go. There's the answer, right? Cool. Good job, us. But before we leave, I would be remiss if I didn't point out we could have done things in a different way, right? So let's suppose we try this alternate approach. All right, so here's an alternate solution. And let's say we didn't know about trig substitution. I know. Do you really want to live in a world without trig substitution? I don't know if I do. But let's pretend we forgot about it. Maybe we saw this on a Calc 1 exam. Do Calc 1 students have the tools to solve this? I think they do. If you were channeling your inner Calc 1, you're like, okay, I love derivatives. It's like, oh, basic integrals and like substitution, right? That's what our inner Calc 1 says. Because that's like the only tool that Calc 1 gave us. So let's do substitution. What substitution to make? There's actually a couple of them that work splendidly. And but again, just pick one. For now, let's go with what's on the inside. Maybe that should be enough. Let's suppose we say u equals 9 plus x squared. All right, because that feels like something a Calc 1 student would try. And if we did that, we say, well, that says that du would be 2x dx. Or if you like, 1/2 du is x dx. And at this point, you're like, well, that's all fine and dandy, Steve, but you got x to the 5th up there. I see where you're coming from. I see what you're saying, but here's a cool fact. It turns out x to the 5th has another name. It's called x to the 4th times x. You're like, oh, well, okay, I'll grant you that. But that's still x to the 4th. What are you going to do with that? Do you see that x squared? X squared is u minus 9. So x to the 4th is u minus 9 squared. Oh, okay, interesting. So that says we can update everything. So this becomes the integral u minus 9 quantity squared. Square root of 9 plus x squared becomes square root of u. I should make my 9s look more like 9s and not like a's. And the x dx became a 1/2 du. And now, if we start playing with this, in other words, just playing called doing algebra. Upstairs we'd have u squared minus 18u plus 81 divided by square root of u. And this is the same as 1/2 integral. And now we just combine. U squared over square root of u is u to the 3/2 minus 18 u over square root of u, u to the 1/2. 81 over square root of u is 81 u to the minus 1/2. And that's something we can integrate. It's all just powers of u. So we say, oh, okay, well, this becomes 1/2 times, add 1 to the power. So 3/2 plus 1 is 5/2. And then multiply by the reciprocal, 2/5, u to the 5/2. Here, we're going to have adding 1 gets us 3/2, multiply by the reciprocal, 2/3, u to the 3/2. And here, if you add 1, you get 1/2, multiply by the reciprocal, you get 2 over 1, u to the 1/2. And then toss on a plus c. And you'll notice that the 1/2 in front cancels with all those 2's. Okay, so they're all gone. And what do we have? Well, what we're left with is we now replace with this u is 9 plus x squared. So this is 1/5 9 plus x squared to the 5/2 minus 18 divided by 3 is 6 times 9 plus x squared to the 3/2. And 81 over 1 is 81. 81 9 plus x squared to the 1/2 plus c. And it's the exact same answer. Now you might say, it's not. It's true. It doesn't look the same, but that's because we haven't done the simplification. If we were very, very patient and ran through the simplification, they would be the same answer. So not everything has to be done with trig substitution. This is just my way of saying there can be other options. I would encourage you to use trig substitution because I think it is very elegant. And there are certain things that are much easier to see and carry out by doing trig substitution than by other methods. But there are alternatives that exist. And so just wanted to make that comment because, you know, we're having fun. We can enjoy ourselves, right? Of course, we should always enjoy ourselves. So the third problem, to find the integral of t to the 4th plus 7t cubed minus 2t squared plus 25t minus 20 divided by t squared times t squared plus 5 dt, we use polynomial division and partial fraction decomposition to rewrite the integral. Find the values of a, b, c, and d so that the expression, you know, what we had up here, has the following partial fraction decomposition. Okay, well, they already told us there's a 1. Well, that's kind of convenient. So we have to find a, b, c, d. Good, good. Well, let's first worry about our long division. And we could do it technically without doing long division, but I don't want to do that. I don't want to do that. And, okay, so I want to practice long division. How does it work? Well, we know what we're dividing by. We know what we're dividing into. So I'm going to think of the denominator. Just make a note here. T squared times t squared plus 5 is the same as t to the 4th plus 5t squared. Okay, so we're dividing that into the upstairs. Okay, so we're taking t to the 4th plus 5t squared, divide into t to the 4th plus 7t cubed minus 2t squared plus 25t, whoops, 25t, sorry, minus 20. There we go. All right, so we say, okay, look at leading terms. T to the 4th, t to the 4th. What do you have to multiply t to the 4th by to get t to the 4th? 1. Haha, that's where that 1 came from, by the way. Okay, now multiply this one by this expression. So that's t to the 4th plus 5t squared. And we're going to subtract. All right, now when we carry out this subtraction, what's going to happen? Well, we're going to be left with 7t cubed minus 2t squared minus 5t squared minus 7t squared plus 25t minus 20. All right, so what does that tell us? Well, it tells us the following. After doing our long division, we're going to have that this expression here looks like 1 plus, and then we're going to have this remainder. So that's our 7t cubed minus 7t squared plus 25t minus 20 divide by this divisor, our t squared times t squared plus 5. Okay? All right. And you can do a matching game, right? So you say, this one here matches with this one here. You can say this remainder here matches with this term in the numerator. And then if I don't run out of colors, this is sort of a different bluish color. What we divide by is what we divide by. All right. They are different blues. Okay, cool. Now, we play our matching game. We say, well, we see that the 1 goes with the 1, which means that all of this goes with all of that. And so they even gave us the form. One of the hardest things about partial fraction decomposition is getting the form right. And we say, okay, they gave us the form. So what are we going to do? Well, we're going to clear out denominators. So here's our basic thought. We're going to say, let's take these two things. We're going to set them equal to each other. So these two things are equal. And then clear out our denominators. So we're going to not worry about the ones. Long division took care of the ones. And what do we get? Well, we'll get that 7t cubed minus 7t squared plus 25t minus 20 is equal to, and so to follow along, we're multiplying everything by t squared over t squared plus 5. So in the first term, the t squared plus 5's cancel. So you get at plus b times t squared. In the second term, the t squareds cancel, plus c times t squared plus 5. And in the last term, 1t cancels. So plus d times t squared plus 5. Now, I like to recommend, there's two options here, right? Make good choices and expand and group coefficients. I like to recommend make good choices. And I apologize, I'm writing uphill for some reason. I don't know. I like to think of it, that's my optimist way of writing, right? Everything's looking up. Okay, so what does make good choices say? Is there a very convenient value for t? Yes, there is. T equals 0 is a wonderful convenient value because you'll notice t equals 0 will zero out something. And so in particular, it will zero out this first part and this last part. So if you plug in t equals 0, lo and behold, you get negative 20 from here is equal to 0 and 0 and 5c. So we say, oh, so that tells us that c is negative 4. Progress. So we can say, okay, replace c by negative 4. Are there other good choices? Not really. Not anything that will zero out a lot of stuff. You might say, oh, but what about square root of 5i? We don't want to go down that road. We definitely don't want to go down that road. So here's where we say, let's shift gears and we'll start grouping our coefficients. So first thing is we need to expand. So we're going to multiply out. So we're going to get, this is the same as at cubed plus bt squared. And there's a minus 4t squared. I'm going to put the powers underneath each other. And there's a minus 20. And let's see, there's a plus dt cubed and a plus 5dt. Okay, all right, good. And so that leaves us with a plus d t cubed, b minus 4 t squared, 5 times d times t, and minus 20. And now, our moment of truth, our coefficients have to match. So we say, well, this coefficient of t cubed over here has to be that coefficient of t cubed. So we say, well, that means that this a plus d has to be 7. That's not very helpful right now, but we keep going. Then we say, well, hey, this coefficient, b minus 4, has to match this coefficient, negative 7. And then we say, well, wait, that is convenient. So b minus 4 equals negative 7. If you add 4 to both sides, that says b equals negative 3. Okay, good. We already got this equals negative 4, so we're like, yes, we're halfway, because we have to find 4 numbers, right? But 4 numbers, there we go. And we got 2 of them. Now, this coefficient of 25, coefficient of t, has to match that coefficient, 5d. So this says, oh, hey, this has to be 25. Oh, well, that's good. 5d equals 25. Turns out d equals 5. 3/4 of the way there. And the minus 20 has to equal minus 20. And I'm like, okay, yeah, that's a freebie. Now, on a side note, you might say, why did that happen? Well, because we already figured out what happens when you plug in t equals 0. Plugging in t equals 0 is the constant coefficient. And I say, well, what's left? We know c, b, d. What's left is a, and we haven't come back here yet. But now we know d is 5. So we say, oh, well, place that in. A plus 5 equals 7. So what is a? It's 2. All right. And we're done. Because the only thing it says is find the values of a, b, c, and d. Doesn't say we have to do anything after we find them. Just says we have to find them. Now, we want to put them together so that our grader doesn't have to hunt for them. Because if they have to hunt, they may miss them. So we'll just put them here on a list. So we have a equals 2. We have b equals negative 3. We have c equals negative 4. And we have that d is equal to 5. So 2 minus 3 minus 4 and 5. And there we go. All right. Now, you may be wondering, did I have to absolutely do long division? Technically on this one you didn't, and there was a way to avoid it. I'm not a big fan, but because I always feel like you should do long division. You should get the hang of it, because sometimes you'll have to do it. So let me just grab a page here. We won't redo the whole problem, but what if it's like, I just really, really hate long division, Steve. Can I avoid it? The answer is yes. And here's how you avoid it. In this case, but that was because they were being nice to you. If they weren't nice, you'd still have to do long division. So here's how we take advantage of their niceness. Notice how you have t to the 4th plus 7t cubed minus 2t squared plus 25t minus 20 divided by t squared times t squared plus 5 was equal to 1 plus at plus b over t squared plus 5 plus c over t squared plus d over t. That's what they said. They didn't quite write it out that way, but that's equivalent to what they said. And here's what you do. You say, well, look, I'm not going to do long division because you already did the hard work for me. Just going to multiply by t squared times t squared plus 5. And if you do that, you'll get t to the 4th plus 7t cubed minus 2t squared plus 25t minus 20 equals, in the first term, you're going to get a t squared times t squared plus 5. And then you'll get an at plus b times t squared plus c times t squared plus 5 plus d times t squared plus 5. Now do the same thing as you did before. Pick nice values, expand, and group. And so technically you can avoid doing long division on this problem if you want to. So just want to make that note. All right, well, good. From here, it's pretty much what we did before, so I won't do it again. So let's keep going. Our fourth problem. Find the integral of dz divided by square root of z squared minus 10z plus 9. And we might look at this and say, oh, this is exciting. Because notice, this factors. Hoo-hoo-hoo! You might say, ah, ha, 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 ha. And we'll get excited because factoring is a good sign, right? Because you might say, hey, this is the integral of dz over, and downstairs, this factors as z minus 1 times z minus 9. True story, true story. And then you're like, cool. But then you're like, wait, what do I do with this? Can we do partial fractions here? No, we cannot do partial fractions here. Partial fractions is out because we have that square root. Can we do anything else? No. So it's cool that it factors, but factoring on the inside is not what we need. What do we need? We need squares. That's not a square. Okay, so unfortunately, this did not pan out. But, it's fun to try things. So it's like, okay, so we won't follow that road. So now what? Well, we start thinking, hey, let's think maybe we can do a trig sub. And we say, okay, well, what do our trig subs look like? We have our couple of trig subs. We'll write them down for reference. We have our u squared minus a squared. I don't know why I start with that one, but that's u equals a secant theta. U squared plus a squared. That's our u equals a tangent theta. And a squared minus u squared. That's our a sine theta. Okay, which one are we in? Now, it's very tempting to say, oh, I see a plus 9, so that looks like plus 3 squared, so this should be my u squared, right? Well, we don't do that. But that's not a square. Z squared minus 10z, this part right here is not a square. So we don't think of it as like, oh, u is the square root of z squared minus 10. No. Oh, no, don't do that. So it's not u squared plus a squared, at least not yet. So where do we need to go? Well, in order to do a trig substitution, we got to get it into one of these forms. So we must complete the square. Now, when we're doing a complete the square, we're going to focus on the things that looks polynomial. So we're going to say, well, that's z squared minus 10z. And we say, what's in front of that z squared? It's a 1. Good news. We like that 1. And we say, all right, suppose I just saw this. Don't worry about anything else. Just this is our focus right now, z squared minus 10z. What do we need to add so that that would be a perfect square? Well, because that's a 1, take the middle term, divide it by 2, negative 5, and square it. Add it on, 25. Because if we did that, this would become z minus 5 squared. Now, back into our problem. So we say, well, we were going to have z squared minus 10z plus 25, but I need to get plus 9. So how do I make a 25 into a plus 9? Answer is subtract 16. Okay, so what do we really have? Well, what we really have is that this is the integral of dz over, and we have the square root of z minus 5 quantity squared, and then minus 16 we'll write as 4 squared. So we're in that form. Okay, so to be more explicit, we have z minus 5 quantity squared minus 4 squared. So here's our u, here's our a. So our substitution is going to be z minus 5, which is our u, is equal to a, which is 4 secant theta. All right, good. So there's our substitution. And you might say, are we allowed to have a minus 5? You betcha. You betcha we are. Okay. Well, if that's a you betcha, then it must be good. Well, okay, now where do we go? We take the derivative, And we say, get dz is equal to the derivative of secant is secant theta tangent theta, d theta. Okay, so that's good. And what does this term become? The square root of z minus 5 squared minus 4 squared. Well, this becomes the square root of 4 secant theta quantity squared minus 4 squared. Well, that is the square root of 4 squared times secant squared minus 1, which is the square root of 4 squared tangent squared, ha ha ha, ho ho ho, which is 4 tangent. The square root goes away. Well, of course it does. That's why we went down this whole process to begin with. Of course it will. Of course it will. All right, so now back to our problem. We are ready to update. So we have integral. The dz becomes 4 secant tangent. So 4 secant theta tangent theta d theta. Downstairs, we have 4 tangent theta. All right, good. And, well, we can cancel the 4's, and we can cancel the tangents. So this is the integral of secant. And now we're like, yes, no tricks, no crazy identities. It's just log secant plus tangent, straight off the formula sheet, right? Of course it is, of course it is. And we're like, huzzah, huzzah, we're done. Or are we? Just when we thought we were out, this problem pulls us back in because we haven't finished. We didn't start with thetas, we started with z's. So we got to end with the z's, which means we got to get our trig on. Okay. Well, let's look at what we have. We have, right here, 4 secant theta equals z minus 5, or, if you like, secant of theta is z minus 5 over 4. Draw a triangle. It's a right triangle. Don't draw the wrong triangle. Draw the right one. Little corner, right angle. Put theta somewhere. Now, secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant's hypotenuse over adjacent. So hypotenuse, adjacent, right? Hypotenuse, adjacent. This last side is the square root of z minus 5 squared minus 4 squared, which, by the way, is this expression, the square root of z squared minus 10z plus 9. That's what started this whole process. All right. Well, we're now ready. With this triangle, we can read things off. So, for example, secant theta, well, we don't have to read very hard. Z minus 5 over 4. So this is natural log of z minus 5 over 4. And tangent theta is opposite over adjacent. So plus square root z squared minus 10z plus 9 over 4 plus c. And that is a correct answer. However, we can do one more thing, and I'm going to do this. This is correct. We could stop here. But notice we can put these over 4's together, and then we have log of something over 4. So we can use properties of log to say this is log of z minus 5. So that's a z minus 5 plus the square root z squared minus 10z plus 9. And then minus log of 4 plus c. But what is log of 4? It's a number. It's a constant. And there's a c here. Constants absorb constants. They're like sponges that way. And so this can get so bloop, and it gets sucked in to that constant. And so my final way I'm going to write this is to say this is log of z minus 5 plus the square root of z squared minus 10z plus 9 plus c. And there we go. That's my final answer. As I said, this would get you full points. But it's nice to sort of understand, like, oh yeah, there's manipulations that can go on, and it's good to see them from time to time, just in case anybody ever pulls it out in the future. And then you have to be like, yeah, I know that. Come on, give me a break, give me a break. But okay, another problem down, which means more problems to go. Let's go. Find the area of the region lying below the curve y equals the square root of 144 minus x squared above the x-axis and to the right of the line x equals 6. Okay, what's going on? What is this? And so let's figure this out. Now, this is not too hard to spot, hopefully. We've seen this kind of function a lot. Y equals square root of 144 minus x squared. If you were to square both sides, this would give you y squared equals 144 minus x squared, or x squared plus y squared equals 144. And that sounds like a familiar number, a number we see a lot. You might say, I don't know, seems kind of gross. Oh, math humor never gets old. Okay, it's 12 squared. And gross, by the way, is another name for a dozen. So one gross means 144. All right, so it's a circle, and it's a circle radius 12. We're like, cool. That helps us explain stuff, and we're in the first quadrant. So we say, okay. Well, how do we know we're in the first quadrant? We should be careful there. Draw a circle, or at least draw a reasonable facsimile to a circle, 12. Now, we're above the x-axis, and we're to the right of the line x equals 6. So you go halfway. Here's x equals 6. And so the part that we're after is this right here. That's what we're after. All right. Good. Now, let's see if we can't figure some things out. Now, I will say that there are some ways to do this which are faster than others, and we can write down the answer without doing any calculus at all, doing just geometry. I know, crazy thought, but it's true. And that is to say, look at our triangle that we form here. And what can you tell me about this triangle? Well, it turns out that very convenient for us, this angle right here, that's a 60-degree angle. Now, you might say, how do you know that's a 60-degree angle? Well, think about it in terms of, let's say, the cosine. So notice that this is halfway. And so if I were looking for this spot, this angle, I'd say, what value of cosine gives me half? And I know that sounds very dramatic, but that's what I'm after. And so it's 60 degrees. And you're like, okay, okay, so how does that help, Steve? Okay, now here's the fun part. Let's imagine you cut out a wedge. In other words, you cut this triangle into 6 equal pieces. Now, the area of a whole triangle is pi r squared, but we're going to divide that into 6 equal pieces. That's the area of this wedge that's been cut out. What's the area of this triangle? Okay, now, this is getting fun. Well, it's what? 1/2 base height. So if you play around with the numbers, we're gonna subtract off this area. So we're going to subtract off 1/2. The base is 6. What's the height? Well, remember how we said cosine helps us figure out where this angle is? The sine helps us figure out the height. So sine of pi 6 is root 3 over 2, but we're in a circle of radius 12, so you got to scale. So the height would be 6 times square root of 3. And so what do we end up with? Well, so our answer will be, here's my prediction, no calculus. If we divide 6 into 12, that leaves me with 2 and there's another 12. So 24 pi. And then here I can cancel at least 1 3 minus 18 square root of 3. So this should be our final answer. That's the geometry talking. Let's do what the calculus talks. All right, so what is the calculus going to tell us? Here we go. We're going to find an area, because it says area. So our area, we're going to go from 6 to 12 of this value, square root 144 minus x squared dx. All right, well, this is very similar to our first problem, so we're not going to do a lot of time humming and hawing. So this is 12 squared minus x squared, which looks like constant squared minus variable squared, which in particular, this kind of situation says the trig substitution should be u equals a sine theta. So for us, u is x, a is 12. So that's our substitution that we want. Dx will be 12 cosine theta d theta. And if we work through the square root of 144 minus x squared, well, that's going to be 144 times 1 minus sine squared, which is going to be square root 144 times cosine squared, which is going to be 12 times cosine. Okay, so this becomes our integral. We have 12 cosine theta. That's that square root of 144 minus x squared. Then we have our dx, which is 12 cosine theta d theta. All right. And now the bounds. Yes, don't forget the bounds. You see, these bounds from 6 to 12, these are x bounds. We don't want x bounds. We want theta bounds. So we have to update. All right, so when x equals 6, well, what does that tell us? That tells us the following. We want to have that 6 equals 12 sine theta, or sine of theta should be 1/2. Now, when does sine of theta equal 1/2? Well, if we look it up, that tells us that theta should be pi over 6. So we write that down, pi over 6. How about x equals 12? 12 equals 12 sine theta. Well, that says sine of theta should equal 1. So that tells us theta should be pi over 2, pi halves. So we write that down, pi over 2. All right, good. Now, we're ready. We now multiply. 12 times 12 is 144. That can come out in front. 144 integral pi over 6 to pi over 2. And we have our cosine squared. What do we do with cosine squared? Power reduction. So this is going to become 144 times 1/2. And then we have pi 6 to pi halves. And where's that 1/2? From power reduction, 1/2, 1 plus cosine 2 theta, d theta. Okay, so we really have 72 times, what's our integral? Theta plus, and then integral of cosine is sine 2 theta. And don't forget to account for that 2 on the inside, 1/2. and evaluate that from pi over 6 to pi over 2. All right. Well, we now plug in, and then we'll be done. We don't have to go back to x because we updated our bounds. So that's why we update our bounds, so we don't have to do more work at the end. We like it when we don't have to do more work. It's one of our favorite things, not doing more work. So we have pi halves. That's good news. Sine of pi, 0. That's great news. Whew, good. So plus 0. All right, and then we're going to subtract. Plug in pi over 6. Pi over 6 plus 1/2 sine of pi over 3. Now, we have to figure some things out. First off, pi over 2 minus pi over 6. Well, if we think of that, we can think of that as 3 pi over 6 and minus pi over 6. So if we put these two together, that would get us to 2 pi over 6, also known as pi over 3. Sine of pi thirds. What's that? Well, we can look that up, and if we look that up, we get square root of 3 over 2 times 1/2. So we get minus from here, 1/4 square root of 3. Okay? So that's that term, and then there's a 72 out in front. Okay, so now I'll distribute the 72 through. 72 divided by 3 is 24. 24 pi. 72 divided by 4 is 18 square root of 3. So our answer is 24 pi minus 18 square root of 3. Who would have thought? What are the odds? They're very high, actually. So yeah, so it just turned out that they picked a very convenient place to cut so that we could take advantage. So in theory, there's a non-calculus way to do it. But that's because we kind of got lucky with the angle that was given where they made the cut, it being halfway in between. If they had cut it somewhere else, it would have been really hard to nail it down. But don't worry, the calculus will not fail us. So it's actually, in some sense, reassuring we got the same answer. It means the process works. The process works. All right, good. Evaluate the integral 0 to pi over 6. And upstairs we have cosine t. Downstairs we have 6 minus 5 sine t plus sine squared t dt. What? That looks crazy. And at first we might say, well, maybe this is like some kind of weird trig identity downstairs, but it doesn't feel like a weird trig identity. But the more we look at it, we say, well, downstairs everything's in terms of sine, and we have a single cosine upstairs. So it's almost trying to sort of hint at what we should be doing. And in particular, we could say, well, another way that we could have written this is 0 to pi over 6 of 1 over 6 minus 5 sine t plus sine t squared times cosine t dt. And so we say, oh, well, since you say it like that, that's suggesting something. What is it suggesting? Well, if we think of this back and this cosine t dt, that could be our du. So and notice the derivative of what? Derivative of sine. So if we put u equals sine t, du equals cosine t dt. Nice. So this will become, if we update, plug in our bounds, right? So sine of 0 is 0. Good. Sine of pi over 6. We look it up. 1/2. Okay, good. It's nice to have a reference, right? And then we have 1 over 6 minus 5u plus u squared du. Okay, That's already looking a lot friendlier. Now, where to next? Well, at this stage we can say, well, can we factor? Yeah, we can, right? Because our calc teachers love us. Because they would never give us something that we couldn't factor, except when they do, and then we complete the square. But let's try factoring. And one thing we could also write is if we write this in our more standard way, oftentimes we prefer to have the powers going down. So it might be easier for us to write as u squared minus 5u plus 6. Because that tends to be how we think, like just highest power, then work your way down. So, does this factor? And how? Well, okay, we need two things that multiply to 6, add to negative 5. Well, I can think of two things that do that. Here, let me pitch you a suggestion. What if we did u minus 2, u minus 3? Does that work? Well, let's check. U squared, that's all good. We're liking that u squared. Minus 2u and a minus 3u makes minus 5u. Minus 2 times minus 3 is 6. Okay, good. So what kind of problem do we really have? Well, this was secretly a partial fractions problem the whole time. And so we're like, oh, well, secretly partial fractions problem. Let's come over here and let's do some partial fractions work. And the good thing is this is a fairly straightforward partial fractions type problem. So we say, all right, we know what we have. We have 1 over u minus 2, u minus 3, which shows us we're going to have two pieces. One of them is going to be u minus 2 downstairs. The other one is going to be u minus 3 downstairs. And the upstairs, we don't know. Not yet, but we will. That's our goal. That's why we're doing all of this. All right, well, clear your denominators. Okay, so if we clear our denominators, and that is to say everything gets multiplied by u minus 2, times u minus 3. Ran out of space there, but imagine I hadn't ran out of space. Then what we would get is that 1 is equal to a times u minus 3 plus b times u minus 2. And I think we can make some good choices here. If we plug in u equals 2, well, we'll get 1 equals a times minus 1, and the b term goes away. So that tells us that a is negative 1. If we plug in u equals 3, 1, that term goes away, and we get b times 1. Well, that tells us that b is 1. So the punchline from doing all this work for partial fractions says, your original expression, which you were having a hard time with, is the same as having minus 1 over u minus 2 plus 1 over u minus 3. In other words, this is a simpler thing to integrate. We like simpler things. And so we're just going to take this and put it into there. All right. So now we update our integral. So this becomes the integral. Bounds stay the same because the only thing we've done is rewrite the function. And all right, so that's minus 1 over u minus 2 and plus 1 over u minus 3 du. All right, good. Now, plug in. Now integrate. So, what do we have? Well, these aren't too bad to integrate. So the integral of 1 over u minus 2 is natural log of u minus 2. And looking ahead, we're going to be plugging in 0. So I want to make sure, if I plugged in 0 minus 2, that would be negative. So I want to make sure I don't end up with negative. So I'm throwing absolute values in. Normally I don't throw absolute values in unless I know I'm going to need them. But I know I'm going to need it. I can just see it coming. All right, evaluate from 0 to 1/2. And now the end is in sight. We just have to clean this up. Okay, so we have minus log 1/2 minus 2 plus log 1/2 minus 3 subtract minus log of minus 2 plus log minus 3, and with absolute values thrown in. Okay, so if we clean this up, 1/2 minus 2, we flip it. 2 minus 1/2, it's -3/2 or +3/2 when we do absolute value. So minus log 3/2. 1/2 minus 3, again, absolute value is going to be 3 minus 1/2. 6/2 minus 1/2, that's 5/2. Plus log 5/2. Minus minus makes a plus. Log of 2 minus log of 3. And we can put all of these logs together. So here's the rule about when you have a bunch of logs. There's no coefficients, so this is going to make it super easy. If there's no coefficients, it's just a bunch of logs being added up. You just say anytime there's a plus, put it in right side up. Anytime there's a minus, put it in upside down. Okay? Because minus means 1 over. Division. Now, you might say, well, Steve, wait, what if there were coefficients? Well, just move the coefficients in first as powers, and then do it. Okay, so here's what I mean. So, term by term. There's a minus. So this term goes in upside down. Okay, flip it over. It's a plus. This goes in right side up. A plus. This goes in right side up. A minus. This goes in upside down. And now you see if you can cancel. I can cancel some 2's. And we're left with log of 10 over 9. And we're done. Woohoo! So that's one of the nice things about logs is that they can be very simple to combine together when you have linear combinations of them. But make sure you know your log rules. And logs are very important, so it's not a bad idea to know your log rules. Okay. Whew! Nice problem. Let's keep moving right along. On to the next problem. We're gonna do more math and have ourselves a good time. Woo, woo, woo. Moving right along, moving right along. Find the exact value of the integral from 0 to 4 of the square root of x squared plus 9 dx. Okay. Whew. All right. Well, I don't know why, but it's like the hairs are standing up. I think something is coming. And you might say, oh, is that Steve's arctangent senses tingling? No. But I think something is coming. All right. Let's go through and do this. Okay, so process. What technique are we thinking of? Well, we say, hey, we see a square root. And it's of a form. We have function squared plus number squared. So it's really trying to be like, oh, use trig sub, use trig sub. Okay, we will listen to your problem. We will do your trig sub. So if we have our x squared plus 9, well, that's really x squared plus 3 squared, where we have u squared plus a squared. Now that tells us we should make the substitution equals a tangent theta. In our case, our substitution will be x equals 3 tangent theta. Now, a couple of notes. We can find dx. That's 3 secant squared theta d theta. Right, derivative of tangent is secant squared. And if you go through and clean it up, square root of x squared plus 9 is 3 secant theta. Okay. All right. Good, good. Well, where do we go from here? We plug it in. We have our dx, we have what that is, and we get the following. We say, hey, we have that the integral 0 to 4 of square root x squared plus 9 dx is going to be 3 secant theta. And I will worry about the bounds in a second. Times 3 secant squared theta d theta. All right, now the bounds. What are the bounds? Well, these are x bounds. All right, so at x equals 0, what do we have? Well, we have 0 equals 3 tangent theta, and so that says that tangent theta is 0, so theta equals 0. Okay, so this was a 0, which oftentimes that can happen. How about at x equals 4? What will that be? Well, you get 4 equals 3 tangent theta. And you might say, aha, that says tangent of theta is equal to 4/3, which tells us that theta is arctangent of 4/3. Okay, we don't know what that is. All right, let's, for the moment, we'll call this alpha, and we'll come back. So 0 to alpha, where alpha is this angle. To help us save space when we're writing. And we'll come back and when we need it, we'll figure it out. All right, so what do we have? Well, we have something that doesn't look too bad. We have integral from angle up to an angle, 0 to alpha, of 9 secant cubed. Now, if you remember, when we had our discussion about trig integrals, when it came to secants and tangents, there were 3 cases. Case number 1, you can pull off a secant squared and write everything in terms of tangent. And that was a beautiful case. Case number 2, you could pull off a secant tangent and write everything left in terms of secant. And that was a beautiful case. And then we had the 3rd case where we wrote the word ugh. And that's a literal ugh. The 3rd case is secants to odd powers. We don't like that. Now, oftentimes what happens when we have secants to, say, secant cubed, they would give us a formula. They were not nice this time. So we are going to have to figure that out. So let's do some work over here. We're going to do the integral of secant cubed. We're going to try to fit it into this little space. So I'm just going to do it without worrying about bounds. So the integral of secant cubed theta d theta. Now, it's not so obvious what to do, but we're going to channel our inner integration by parts. So this is, the way we do this is integration by parts. Now, why does that have a chance? Well, because there's at least a part of it that's an easy thing to integrate. So remember, in integration by parts, you're taking a derivative of one thing and integrating another thing. So something has to be easy to integrate, something has to be easy to take a derivative of. Now, trig functions are generally speaking easy to take derivatives of. So is there something easy to integrate hiding in among the secant cubed? There is, and it's called secant squared. And so, with that in mind, we say, oh, well, we're going to have this last part be the thing we integrate, and this first part be the thing that we differentiate. So that tells us then that our du, derivative of secant, is secant theta tangent theta d theta, and our v, the integral of secant squared, is tangent. So what do we have? Well, we have uv, secant theta tangent theta, minus integral v du. So we have secant theta tangent squared theta d theta. Now, you might say, well, we could have a secant tangent and play with that. But here's where the magic comes in. after we do one round, now we're going to say, wait a second, a tangent squared. We have a nice identity. Tangent squared, we can write that as secant squared minus 1. So suppose we were to write that in. And what would happen? Well, we'd have the following. We'd have secant theta, tangent theta, minus, okay, so we're going to think of it as secant times secant squared. So that's the secant cubed. So I'm going to write that as one of the integrals, secant cubed theta. And then minus minus makes a plus, the integral of secant times 1, so integral of secant theta, d theta. Okay, now the grade O, because we deserve a grade O at some point. We say, haha, this looks suspiciously similar to that. So we're going to move that over, and that part we can at least integrate. So if we carry out those two steps, we get the following. 2 integral secant cubed theta d theta. Okay, so that those two combined, because this is a minus, this comes over as a plus, is equal to secant theta tangent theta plus, and the integral of secant is log of secant plus tangent and plus c. And so finally, dividing through by 2, the integral of secant cubed d theta is 1/2 secant theta tangent theta plus 1/2 log secant theta plus tangent theta, and then plus 1/2 c, but c is a constant, can absorb constants, so plus c. All right, good. So what do? We're just going to literally just plug that in. We have the antiderivative of secant cubed. We worked hard. We should celebrate our victory. So we have a 9, and we can multiply the 9 through, so we get 9/2 secant theta tangent theta plus 9/2 log secant theta plus tangent theta. And we don't need the plus c because we're doing a definite integral. We just need to evaluate from 0 to alpha. Now some good news. Plug in the 0. Tangent of 0 is 0, knocks out the first term. Secant of 0 is 1. Tangent of 0 is 0. 1 plus 0 is 1. Log of 1 is 0. That knocks out that term. So when you plug in 0, poof, it's all gone. So we just got to plug in our alpha. Okay, so we have 9/2 times secant alpha tangent alpha plus 9/2 log secant alpha plus tangent alpha. Okay, nice. And we're ready. Why? We just need to figure out what these numbers are. Remember, we said alpha, that was here. Okay, so we're going to draw ourselves a little triangle. And so here, this angle is alpha. So we say, okay, tangent is opposite over adjacent. 3, 4, 5. 3, 4, 5 triangle. Oh, that's nice. Oh, wow. Okay, 3, 4, 5. Okay, sorry. What's secant? Hypotenuse over adjacent. So secant is going to be 5 over 3. Tangent is opposite over adjacent. 4 over 3. Secant, we already said 5 over 3. Tangent is 4 over 3. So what do we have? Well, in the first case, we're going to have 9/2 times 5/3 times 4/3. Now, if we carry this through, you'll see we get a lot of cancellations. The 9 cancels with the 3's. 2 goes into the 4, which leaves us with 10. plus 9/2 log 5/3 plus 4/3 is 9/3, also known as 3. So 10 plus 9/2 log 3. And that's our answer. Whew, that was a workout, right? Well, yeah, when they don't give you the formula for secant cubed, it can take a while. And so hopefully they're nice and they give us the formula for secant cubed. But if they're not, well, we should at least do that computation once in our lives, right? It's good to say, yes, I remember the day I integrated secant cubed. It was a wonderful day, a beautiful spring day. All right, well, let's keep on going. So our 8th problem says find the integral from 0 to 2, 4 minus 3u squared over 4 plus u squared squared du. All right, now, you might say, can we do some partial fractions type thing? And you can do a little tiny bit, but not as much as you think. So this is not really a partial fractions. In some sense, this is the kind of integral you'd have to deal with after doing a partial fractions. And you say, well, wait, if it's not partial fractions, what do we have? Well, so here's the thing, is most of the time when we think of trig substitution, we are looking for a square root. But there's essentially one exceptional case, and it's this kind of situation, when we have an a squared plus u squared downstairs. So this is a good candidate for trig substitution. All right, well, with that in mind, we say, okay, well, what do we have here? Well, we really have 2 squared plus u squared, which looks like a squared plus u squared. And now what's the substitution that we make? In this case, we do u equals a tangent theta. So we're going to say, we'll let u equal 2 tangent theta. So there's our substitution. And we don't have any square roots, but we'll still do a couple of things here. We'll note that du, derivative of tangent, is secant squared. Okay, because we'll need that. And we'll make a note that says, well, what happens if we have 4 plus u squared? So 4 plus u squared is 4 plus 4 tangent squared, which is 4 times 1 plus tangent squared, which is 4 secant squared. All right. Well, now, with that out of the way, we're ready to go through and update. So we have our integral. This becomes the integral, and we'll worry about the bounds in a second. We'll have 4 minus 3 times 2 tangent theta squared over, and 4 plus u squared became 4 secant squared squared. Oh my goodness, that's a lot of secant squareds there. And then du is a 2 secant squared. Well, that'll help. All right, now those are the function parts, and I should have said I need to write the d theta. Okay, so we got the 4 minus 3u squared, 4 plus u squared squared, du, the bounds. Don't forget the bounds, right? Because this is a definite integral. We want to update our bounds so we never have to go back. So we say, okay, well, at u equals 0, well, what happens? We get 0 equals 2 tangent theta. And so that tells us that theta equals 0. At u equals 2, we get 2 equals 2 tangent theta, which means tangent of theta equals 1. And so that tells us that theta is pi over 4. Okay, so our bounds are pretty nice bounds. They were pleasant bounds even. 0 to pi over 4. All right, good. Well, let's start cleaning up, see what we have here. And, what can we say? Well, we have integral 0 to pi over 4. And we'll write this as 4 minus 12 tangent squared theta. Okay, that's that part. 2 squared is 4. And so 3 times 2 is 2. Sorry, 3 times 4 is 12. And there's a 2 secant squared. Now downstairs, this is 16 secant to the 4th theta. And all right, well, cancel when you can. And we can cancel, right? So that's good. We're, channel our cancel culture kind of thing. We can cancel 2 of our secants. We can cancel 1 of our 2's. And so that's looking promising. And so at this point we say, well, that's nice. That's very nice. And I also see that these have everything that we have here is factors of 4. So I'm going to pull a 4 out from the upstairs and 8 out from the downstairs. And if I pull out 4 over 8, that's 1 over 2. Integral 0 to pi over 4. And then we have 1 minus 3 tangent squared theta over secant squared theta. All right, good. And I'll just make a little note here. This was a 4 over 8. That's where that came from. Well, what can we do? And one thing we can do is say, well, hey, let's put everything in terms of sines and cosines. Because we like tangents and secants when they're both in the numerator. But when they're not, it can get a little messy. And so what happens? Well, if you look at that secant squared downstairs, it's going to become a 1 over cosine squared, which moves upstairs as cosine squared. Nice. So this becomes 1/2 integral 0 to pi over 4. So we have 1 minus 3 sine squared over cosine squared times cosine squared over 1 d theta. And, well, okay, at this stage, we say, well, this is really 1/2 integral 0 to pi over 4, and we can distribute. So this is cosine squared minus 3 sine squared. Now, if we were in a nicer world, if this had been just cosine squared minus sine squared, we'd be really excited because then we're like, double angle! We've got a double angle! But we don't have that. But what can we do? We can do power reduction! We have a power reduction! Yes, we can do exactly that, Steve. And be calmer. I can. This is so exciting. Okay, all right. We must calm ourselves. Because when we're too excited, we make mistakes, right? Take our time. Enjoy the process. Cosine squared. What happens to that? Well, cosine squared becomes 1/2, 1 plus cosine double that angle, 2 theta. Okay, so we have that. Minus 3. Sine squared is 1/2, 1 minus cosine double that angle. All right, and make sure we have enough parentheses and brackets. And we're almost there. We can go ahead and pull out that 1/2 again during the other 1/2. So we have 1/4 integral 0 to pi over 4. And what do we have here? Well, we have 1 minus 3. -2. Cosine 2 theta plus 3 cosine 2 theta. So that's plus 4 cosine 2 theta. All right. Well, I think we're ready to integrate. All right, so integrating. That gives us 1/4. And then we have minus 2 theta plus 4 times integral cosine is sine. Don't forget to account for that too. So put a 1/2 and evaluate 0 to pi over 4. Well, okay, the 2 goes into the 4. Then these 2's can come out, which makes it really, what do we have? A 1/2 times sine 2 theta minus theta, and evaluate from 0 to pi fourths. Okay, moment of truth. Plug in 0. 0 minus 0. 0. Nice. Plug in pi fourths. Pi fourths times 2 is pi halves. Sine of pi halves is 1. So we end up with 1/2 times 1 minus pi over 4. Or if you like, this is really 1/2 minus pi over 8. And that's it. We did it. Woohoo! All right, good. So a wonderful example of how trig substitution works really well. And so in particular, this is the special case. And to emphasize, what is this special case? This is when you have that irreducible quadratic thing going on downstairs. 4 plus, a squared plus u squared to some power. Then trig sub can help you work through what's going on. All right. Nice. Let's keep on going. Woohoo! Yeah! A thin metal plate of density 2 is shaped like the region bounded by the graph of f of x equals x squared minus 4 divided by x to the fourth minus 8x squared minus 9, the x-axis, and the vertical lines x equals 1 and x equals 2. Find the moment of the plate about the y-axis. Okay, so let me talk about what's going on. Now, we don't need to know it exactly, but we can say, well, suppose we sort of give ourselves some intuition. Here's 1, here's 2. It's not too hard to see if you plug in 2, you get 0. And if you plug in 1, it looks negative upstairs. It's also negative downstairs, so it's actually positive. So it's coming down, something like this. Okay, so we have, this is our thin metal plate. Okay, so we have this shape. And now we say, okay, great. What's our goal? We're trying to find the moment. And not just any moment, a very specific moment, y-axis. So we're looking for m sub y. Okay, so we say, let's think about that. Now, when we think about moments, we should write down the formula to help remind us. We add up individual moments. So we're adding up our pieces. We have a distance, which really should be location, but let's call it distance because that really helps. We have ourselves a density, and we have ourselves a height, and we have our width. Okay, so that's the generic formula. And the way we think about it is we're going to take our region, and it's going to be cut into little tiny pieces. And we say, okay, what's that piece's moment? And then figure it out. Now you might say, how did you know to cut it vertically? Well, because it gave us it as a function of x. We do not want to try to solve for this as a function of y. That, I don't want to say it's hopeless, but it's very close to hopeless. And so we say, okay, so we have our nice rectangles. Now, y-axis. So the question is, how far is the y-axis to the rectangle, and in particular, to the center of the rectangle? Well, the answer is, it's x. Because when we think of slicing, we're thinking of slicing at a generic location, x. Okay, so we're going to go through and fill in these pieces. Well, our A and B, that's where we start and stop the region. So that's at, whoops, not 0, it's at 1, 2. Distance, x. Density, 2, because we gave it to us. It was a freebie. The height is the function. So that's our x squared minus 4 divided by x to the fourth minus 8x squared minus 9. And then the width is this little tiny piece, dx. All right. So there we go. There we go. All right. Well, so if we clean this up, this becomes the integral 1 to 2 of 2x times x squared minus 4 divided by x to the fourth minus 8x squared minus 9 dx. All right, So what is our setting? What tools do we need? Well, we look at our problem. We say there's a polynomial upstairs. There's a polynomial downstairs. Partial fractions. Oh, yeah. Partial fractions it is. So let's do it. And say, okay, well, good news is no long division. Bad news is we've got no factoring downstairs, so that we have to do some factoring. But notice everything downstairs even powers. So this looks like an x squared minus 8x squared minus 9. So if you sort of channel and say, well, let me just think about this as like a y squared minus 8y minus 9, you could probably factor that. Because that factors not too badly. It's y minus 9 and y plus 1. And now go back to x. So this is really x squared minus 9, x squared plus 1. And we like progress, but we can go further. X squared plus 1 can't go further without making it complex. But x squared minus 9, we can do stuff there. X minus 3, x plus 3, x squared plus 1. Okay, so here we go. Let's do our partial fractions. And on a side note, we're going to do this a second time. So if you're like, why is he doing it the hard way? There's an easier way to do this. But hold on. Let's first do it this way, and then we'll come back and say, oh. But let's pretend like we don't see that yet. And if you want, you can skip ahead, or you can be like, what? Wait, what? There's an easier way? Okay, so partial fractions work. What do we have? Well, upstairs we have 2x cubed minus 8x. All right, distribute the 2x through and divide that by our x minus 3, x plus 3, x squared plus 1. And that's going to look like, well, we're going to have something over x minus 3, something over x plus 3, and then we have something over the x squared plus 1. But because that's an irreducible quadratic, it's cx plus d. Remember, there's a good rule of thumb. The number of unknowns, so number of, in this case, letters, has to match the degree downstairs. So there has to be 4 unknowns. If you have fewer than that or more than that, mistakes were made. All right, now clear denominators. And what do we get? Well, we're going to get 2x cubed minus 8x is equal to a times x plus 3, x squared plus 1, plus b times x minus 3, x squared plus 1, plus cx plus d times x minus 3, x plus 3. Okay, good. Now, at this point, you're probably thinking, not so good, Steve. This looks like it's going to take us a while. Well, let's make some good choices. Let's plug in x equals 3. And if you plug in x equals 3, 2 times 3 cubed, that's 54. And then minus 8 times 3, that's 24. And 54 subtract 24 is 30. And, okay, that's still there, so equals, we have a times 3 plus 3 is 6, 9 plus 1 is 10, and so we get a times 60, b times 0, cx plus d times 0, so we say, a equals 1/2. Okay, well, that's good. Is there another good choice? Negative 3. Well, okay, so we plug in negative 3, we get negative 54, plus 24 is negative 30. That term goes away. How about this term? Well, we get negative 3 minus 3 is negative 6, and then 9 plus 1 is 10. So we get, b times negative 60. that term goes away. So we say, so b equals 1/2. Now, are there any other good choices? Well, actually, we know what a and b are. We're just down to c and d. So there's at least one more good choice. 0. 0 is a very popular choice. So plug in 0, you get 0 equals a, which is 1/2, times 3 times 1, so that's 3. And then b, which is 1/2, times minus 3 times 1, which is times negative 3. So these cancel. Plus d, because the cx is gone. And negative 3 times 3 is negative 9. So d times negative 9. So that tells us that d is 0. Okay, so now we know a, b, and d. So what's left? C. And you might say, now I have to work. But actually, it's a freebie. Plug in any number. And you're like, really? Any number? Any number? Any number? I said any number. Because you know what A, B, and D are, you only have C. You only need one more piece of information. All right, how about we pick 2? You might say, why did you pick 2? I just needed a number, and 2 is very convenient because if you look here, 2 times 8 minus 8 times 2 is 0. Okay, equals, A is 1/2, and then we have 2 plus 3 is 5, and then here we have 2 squared plus 1 is 5, so 1/2 times 25, plus b, which is 1/2, 2 minus 3 is minus 1, then 2 squared plus 1 is 5, and then plus c is 0, d is 0, so we have plus 2c times minus 1 times 5. Okay, so we have 25 halves minus 5 halves is 20 halves, which makes this 10 from these two terms here, minus 10c. So that tells us c equals 1. Okay. Whew. All right. Now, what does all of this give us? All of this work is to say the following, that this is the integral, 1 to 2, and we replace what we know. So a was 1/2. So 1/2, 1 over x minus 3. b was 1/2, plus 1/2, 1 over x plus 3. And then we have cx plus d. Well, c was 1, so we get plus 1 over x squared plus 1. Oh, sorry. C is multiplied by x, so 1x. Oh my gosh, you'd be surprised how often that mistake gets made. Make sure you put the right number with the right place. That is one of the most common mistakes in partial fractions. And so it's good to double check. Okay, so we have all our pieces in place. The end is in sight. And now we integrate all these pieces. And we say, okay, so this is equal to 1/2 log absolute value of x minus 3, 1/2 log x plus 3, and the integral of x over x squared plus 1, it's actually, if you multiply here by a 2 and then a half in front, it becomes 1/2 log of x squared plus 1. Because if the derivative of x squared plus 1 is 2x. And we need to evaluate this from 1 to 2. Well, everything has a half in front, so let's just pull that out for the second, and we'll put it in later. Okay, so we start going through. 2 minus 3. 2 minus 3 is negative 1, so absolute value log of 1. 2 plus 3, 5. 2 squared plus 1, 5. Okay, so that's plugging in the 2. Subtract. Okay, 1 minus 3, negative 2, but absolute value makes 2. 1 plus 3 is 4. 1 squared plus 1, 2. Okay, so we now channel our inner properties of logs. Log of 1 goes away, yes, but there's more to it. What can you do? Well, anything that's being added goes in upstairs, so there's a 5 and a 5. Anything being subtracted goes downstairs, a 2 and a 4 and a 2. And so we can say, oh, well, this is really 1/2 log of 5 squared is 25, and 2 times 4 times 2, that's 16. Okay, 25 over 16. Well, we can simplify that because these are both squares. So we could say, oh, this is 1/2 log of 5 over 4 squared. Bring the 2 down, and we get log of 5/4. Done with round 1. Okay, so the answer should be log of 5/4, barring any mistake. Now, I said there was another way to do this, because this seemed to be a lot of partial fractions. We can take advantage of the situation that we have here. Now, what we're about to do can't always be done, but you should always be on the lookout for saying, maybe there's a better way. Because if there is, oh, you're going to feel so good about it. So I'm going to cover up all this work we did here, and I'm going to join the problem mid-problem. Okay, suppose this is the integral we want to carry out. Integral 1 to 2 of 2x, x squared minus 4, divide by x to the 4th minus 8x squared minus 9. Now, did you notice how we said, hey, you notice how everything has like an x squared in there? We did say that. And notice how all these things look like x squared, except for this. 2x. What's true about 2x? Well, 2x is the derivative of x squared. Let's make a substitution. So let's let u equal x squared. Okay, so then du is 2x dx. So that's going to take care of this 2x dx. That's become our du. And let's see what happens. So this will become the integral. Now, these are our x bounds. So this is x equals 1, x equals 2. So what are our u bounds? We'll square that. 1 squared is 1. 2 squared is 4. All right, upstairs, the 2x dx becomes the du. Anywhere else where we see an x squared, put a u. So we have upstairs, we have a u minus 4. Downstairs, x to the 4th, that's u squared minus 8u minus 9 du. So we can solve this problem. And what do you notice about this one? It's partial fractions, but it's an easier partial fractions. We like easier. Okay, that's our motto. And indeed, a lot of math is just saying, hey, let's take this complicated thing and write it in a simpler way. I have to be careful. My u's and my 4's are getting suspiciously like each other, so I have to be really careful to make sure that's a u, that's a 4. Don't confuse it. We can factor. This is u minus 9, u plus 1. You can check. You get u squared plus u minus 9u, and then minus 9. And we say, okay, great. And now let's do some partial fractions work. Okay, so we're going to do some little work here on the side. And, all right, So we have u minus 4 over u minus 9, u plus 1. Well, that's something over u minus 9 plus something over u plus 1. Clear your denominator. Absolutely. And what does that lead us to? Well, it leads us to the following scenario. U minus 4 is equal to A times U plus 1 plus B times U minus 9. All right. Well, make good choices, right? Like taking calculus, great choice. Wonderful choice. So at this point, we can plug in minus 1. And what happens? We get minus 5, minus 1 minus 4 is equal to A times 0. And then we get minus 10B. So B is 1/2. And in a similar way, we say, okay, plug in U equals 9. 9 minus 4 is positive 5. 9 plus 1 is 10, so 5 equals 10A. So A equals 1/2. All right, now all of this is to say the following. We can rewrite our expression in a simpler way, right? That's the whole goal of partial fractions. Rewrite things in simpler ways. So we have that this becomes the integral 1 to 4 of, we have ourselves 1/2 times 1 over U minus 9, and then plus 1/2 1 over U plus 1 du. All right, well, pull out the halves, and well, we can integrate. So this is 1/2 log U minus 9 plus 1/2 log U plus 1. And we have to evaluate 1 to 4. Well, as we did before, I really will pull the 1/2s out. And so 4 minus 9 makes 5. Let me take absolute value. 4 plus 1, 5. Okay, so there's 5 plus 5, subtract. 1 minus 9 is 8. 1 plus 1 is 2. And we do the same thing we did before, namely, we say, okay, the pluses go upstairs, the minuses go downstairs. So we really have what? We have 1/2 log 25 over 16, but that's the same as 1/2 log of 5 over 4 quantity squared. The 2 comes down, so we end up with log of 5 over 4. And if we pull this aside, it's the same thing. Of course it's the same. It's just a different way. So what was our advantage here? Our advantage was that by making a substitution early, it simplified the process. And so oftentimes, look early. The small investments at the start have big payoffs later on. So it's always good to sort of keep your eyes open and say, my goodness, can I do it a little bit simpler? Maybe. Okay, good. Let's keep going because there's one more problem left. Let A be a number between 0 and 6. Find the length of the curve y equals the square root of 36 minus x squared between x equals 0 and x equals a. Your answer should be expression in terms of a. Okay. Now we say, well, length. Now, there's lots of length, but this is y equals f of x. So our generic formula for length in this case is we're going to add up our little pieces of length, and our little pieces of the length look like the square root of 1 plus f prime of x squared. All right, so that's what we're going to have to compute. So, well, we just go for it. Now, in our case, unfortunately, a has a different meaning here. We're saying we're going between 0 and a. So we're integrating 0 to a, square root of 1 plus, now take the derivative. So our f of x is 36 minus x squared to the 1/2 power. So when we take the derivative, the 1/2 comes down. 36 minus x squared to the minus 1/2. And now times by the derivative of the inside, which is negative 2x. And that is going to be squared. Okay. Whew. Well, what's going to happen? Well, a couple of things will happen. The good news is the 2's cancel. That's good news. The minus won't matter. And so when we square this, and don't forget your dx, so integral 0 up to a square root of 1 plus, the x will be on the top, so that'll be an x squared. And then this 36 minus x squared to the minus 1/2 will become 36 minus x squared to the minus 1, which means it's down here as a 36 minus x squared. Okay. Well, let's add the fraction. So common denominator means we're going to replace this 1 here in the front. This is going to become 36 minus x squared over 36 minus x squared. All right, so if we get common denominator and add, well, what do we have? This is the integral 0 to a of the square root. The x squareds are going to cancel, so we'll have 36 upstairs, and then we'll have our 36 minus x squared downstairs, dx. So it's integral 0 up to a of 6 square root 36 minus x squared dx. All right. Good. Good. Now, what kind of problem do we have? So we had a length, and we've set it up. So now it's a length problem, yes, but when I say what kind of problem do we have, it's like, what kind of technique do we need? It's not too hard to see. This is heading in the direction of trig substitution, because we see a square root, and in this case we see a square root of a squared minus u squared. And we say, oh, we know how to handle that because we've seen these before. So when we see a squared minus u squared, that says that we should set u equals a sine theta. Now in our case, we have it's 6 squared minus x squared. So what we have is that x should equal 6 sine theta. That will tell us that dx becomes 6 cosine theta, d theta. And if you work it out, and we've done it so many times already today, that we'll go ahead and just say that the square root of 36 minus x squared also turns out to be a very nice thing. And in particular, it turns out to be a cosine. So we say, all right, great news for us. Everything becomes nice and easy, and we can simplify. Okay, so we have that this is equal to the integral of, we have 6 over 6 cosine theta. Dx is 6 cosine theta d theta. But we're not done. The bounds, don't forget the bounds. Okay, so the bounds. That's going to be a little bit trickier, but not too bad. We know x equals 6 sine theta, so at x equals 0, we're told that 0 equals 6 sine theta. So that says sine theta equals 0, which says theta equals 0. Okay, so that's our lower bound. What about at x equals a? Well, we're told a equals 6 sine theta. So sine of theta equals a over 6. So theta is the arc sine of a over 6. Okay, well, that's an angle. That's certainly true. Arc sine of a over 6. Well, not to beat around the bush very much, but those terms cancel. It becomes a very easy integral at this point. It's the integral of 6, our favorite type of integral. So we get this as 6 times theta evaluated from theta equals 0 to theta equals arc sine of a over 6. And if we plug in 0, you get 0. And otherwise you get 6 times the arc sine. Whoops. My paper's trying to escape. Don't escape, paper. We're almost there. We're near the end. Of a divided by 6. And whew, good. Whew. Now, before we celebrate, but we should celebrate a little bit, so, okay, mini celebration. We can do this without any calculus at all. And you're probably like, come on, Steve. Let us have our joy. We love our calculus. Let's talk about the picture. So what's going on here is we have this curve, y equals the square root of 36 minus x squared. And it's really part of a circle. Okay, so it's part of a circle of radius 6. Now, we're going out to some point A. And so let's say this is our A. So the question is, what's this length? Now here's what we can do. Let us suppose for a second we knew this angle. Let's call this angle alpha. Now what's true is that if we look at the length of that curve, divide by the total length around. So that's another name for the circumference, which is 2 pi times 6. Well, that would be equal to the same as this angle alpha is over a full revolution, over 2 pi. So that tells us that our length is equal to 6 alpha. All right, and you're like, I'm okay with that, Steve. But how does that help us? Well, come here and let's look at this triangle. We know 2 of its sides. This side is A. The hypotenuse is 6. We also know 2 angles, the right angle and alpha. So this alpha matches that alpha. Now look at the picture. What sides do we know in relationship to alpha? We know opposite and hypotenuse. So sine of alpha is the opposite over the hypotenuse. Well, now solve for alpha. That says that alpha is equal to arc sine of a over 6. And you put these two together, and you get that the length is equal to 6 arc sine of a over 6. And so you can, again, do this problem without any calculus. But, of course, on the quiz, if you see such a problem, channel your inner calculus, because we want you to be showing off your beautiful calculus skills, because you've worked hard on these skills. You should be proud of them. You know, this takes work. It takes effort. And we are so happy that you're doing that work, that you're doing that effort. So thank you, thank you, thank you. Keep up and keep going. You can do this. We believe in you. We believe in you. Thanks for joining me, and I hope we'll see you again. Bye.